So now let's give you a background on GPUs here. So GPUs are fundamentally architectures for drawing triangles fast. So what a GPU is designed to do is take a bunch of triangles like this, and for each pixel in the triangle, it's going to run a program to generate a bunch of pixels like this. So in order to do this, you have to take all these triangles, you have to project them into 2D, find the pixels for each one, and then figure out the color at each pixel. If we look at the requirement for this, if you have an average scene with maybe 10,000 triangles in it, you have to do all the work to figure out where those triangles are, and then we want to render it at high definition with a lot of oversampling. So with this much oversampling at this high resolution, that means we've got 18.4 million individual pixels that we need to render for the entire screen. And for each one of these pixels, maybe we do 7 texture lookups and a whole bunch of shader operations, and we want to do this at 60 frames per second to keep people happy. So that's a huge amount of computation and memory bandwidth that's required to do this. And in fact, if you look at the computation amounts and the memory requirements for doing this, it's larger than what you would find in most CPUs. So this is why people are excited, because it looks like there's a lot of potential to do compute in here because we're doing graphics. So why do we care about drawing triangles fast? Well, let's take a look at the two most popular games for the past 2 years, Grand Theft Auto and Call of Duty Black Ops something or other. This game here made $800 million, and this one made $500 million. And what's important to realize is this was in the first 24 hours they went on sale. So why do we care about GPUs and drawing triangles fast? Well, it's all about money. In fact, it's about lots and lots of money. To put these numbers in perspective here, NVIDIA's quarterly revenue was $800 million. That means this one video game in 24 hours sold as much as NVIDIA does in an entire quarter. Now granted, it took them a while and a lot of money to make the game, but these are huge amounts of money that are in video games, and that's why people are pushing graphics so much. So let's take a look at an example of the sort of computation that GPUs do. So here's the shader for calculating the water down here. Take a look at the source code here. This is the program that is run for every single pixel in the water here to determine the color. So we can see here we've got a lot of these float 3 and float 4 vectors, and in fact we're even returning a float 4 vector. So a question about this, why do we have float 3 and float 4 vectors in graphics? Well, the reason for this is we use lots of 3 and 4 wide vectors. If you have colors, red, green, blue, that's usually 3 values to represent the color or coordinates x, y, z, or colors with an alpha channel or normalized coordinates. And in fact, some GPUs go so far as to actually optimize their architecture for floats of about this size. And that means they can run faster when you're doing graphics, but hurts them in more general purpose uses. If you notice up here, this also returns a float 4. And the reason this program returns a float 4 is it's determining the color. So it's going to return the color for each of the pixels here. We have a lot of other things that are going on in this program. One of the main things here, if you look at all these text 2D calls here, these are going and looking up textures or colors from images loaded on the GPU. But they're not just doing a straight up memory access. So if I want to do a texture lookup, I've got a whole bunch of pixels stored in memory, but I usually want to access a pixel that doesn't line up perfectly with the pixels in the texture. So maybe I want to get the color at this coordinate when I've got colors at these coordinates in memory. So in order to do that, I have to load a whole bunch of pixels and interpolate between them, load more pixels, interpolate between them, and do a final interpolation. So each one of these texture lookups can involve 4 memory reads and a whole bunch of floating point adds and multiplies. So there's special hardware to support that, but the point here is you're doing a lot of data accesses here. We also have math functions. So here's POW and LERP. And if you've never looked inside a math library to see how these things are implemented, then you probably don't appreciate how much code goes on in these. These are hundreds of instructions in order to calculate these things here. So there's a lot of work going on inside those. In addition to that, we have a whole bunch of control flow here. So this looks just the way you'd expect from a regular program. So if we look at what we can do on GPUs, we've got vectors. There's a lot of emphasis on vectors for graphics. But in these texture lookups, these are all specialized to graphics, but then you've got all sorts of other stuff, complex math, function calls, control flow, all the things that you'd expect in a general purpose processor. And that's why people want to try and use them that way. So GPGPU, general purpose GPUs. And I'd caution you, don't use this term if you're writing a paper. These days, GPGPU is sort of out of date. It's just GPU. Here's the question. Can we use GPUs for non-graphics tasks? Well, there are a bunch of answers for this. Yes, they can be incredibly fast and awesome. And this is the case if either you work for NVIDIA or you're doing something that looks a lot like graphics. But there are other answers. Maybe. So GPUs can be very fast, but they're also really hard to program. And this is the case for most people. You can get a significant acceleration in your program, but it's a lot of work. And there's a real question, is it worth the work for the acceleration you get? Now, there are other answers. Not really. It may be that you have an algorithm that's slower on the GPU than the CPU. As we'll see later, GPUs have tiny caches. If your algorithm relies on a cache, it may not run well on a GPU. And finally, the answer may be no. You may need something that isn't present on the GPU, such as more precision, memory, or synchronization. So depending on the type of program you have and how much money you're prepared to pay to rewrite the program, GPUs could be great for you, or they might not be useful at all. So before we go further, I want to emphasize one important thing here, and that's the Achilles heel of GPUs. GPUs are very fast, but getting data to the GPU is slow. To make this point, let me say that again. Getting data to the GPU is slow, and conversely, if getting data to the GPU is slow, then also getting data from the GPU is going to be slow. So let's take a look at how this is today. So in a system today, we may have a whole bunch of DRAM in our system, we've got a processor that's connected to it, and then we've got our GPU, and it has its own dedicated graphics memory over here. Now let's look at the bandwidths between these components. So the CPU, the DRAM, we have a pretty good amount of bandwidth here. Between the GPU and its graphics memory, we have tremendous bandwidth. But then if we look at what it takes from between the GPU and the CPU, we have a teeny amount of bandwidth. So these lines here are to scale. About 50 gigabytes per second between the CPU and DRAM, and over 250 between the GPU and its memory, but between the GPU and the CPU, we're around 10 gigabytes per second. So really slow. So please keep in mind that today the biggest problem with using GPUs to accelerate is exactly this. Getting data to the GPU is slow.